Okay, this video will cover the worksheet 6.4. We'll be focusing on how to answer structure question that asks you on energy conservation, asks you to describe energy conservation. So before we begin, I will just want to highlight some of the terms that we will be using. So when you learn about the principle of energy conservation, there is this term called an isolated system. So what is an isolated system? Basically, a system refers to a phenomenon. So this phenomenon could be as simple as you have a ball, and then you launch the ball at a certain starting velocity. And because you launch it at a starting velocity, it will process kinetic energy. And as the ball goes up in air, the speed will slow down, and at the maximum height, the ball will come to rest. And basically in this system, we say that, well, the total amount of kinetic energy at the start has been converted to gravitational potential energy when it reaches the top. So a system can be anything, but it refers to an object whereby the energy just convert from one form to another, and there is no transfer in or transfer. There's no energy transfer in or transfer out. So as we learn more about energy, we also come across this term called work done. So what is work done? This very special term has puzzled a lot of students because it doesn't sound like energy. But in essence, work done is just an amount of energy that transfer in, or it can refer to an amount of energy that transfer out of a system. So now if you look at the example I gave you, the ball was launched from the floor, right? At first, the ball will be resting on the floor, and then after that, it was being launched with a certain velocity. So from the state whereby it is simply resting on the ground to when it is being launched with a certain velocity, there must be an energy input to this system, right? So we say that the amount of energy that has been transferred into the system, it is called work done. So if you do not like the name or the name confuse you, you can substitute this term in your mind by saying that, oh, okay, this is just energy that has been transferred into the system. Well, similarly, in our daily life, when an object is being launched into the air at a certain speed, there will be air resistance acting against it. So in this case, when you launch the ball with a certain amount of KE, that amount of KE will not only be converted to only GPE, but at the same time it will spend some energy to overcome friction, right? However, when you want to answer structure question, you cannot say that energy is being spent to overcome a force, because energy is in joules, but a force is in Newton, right? So similar to work done being interpreted as energy transfer into a system, to describe energy that has been transferred out of the system, for example, the energy that's been transferred out in this particular case is that some energy will be transferred to air, right? So we say that this is also called work done. So in essence, work done can refer to energy that is being transferred in or transferred out of the system. When you have energy transfer out of the system, we say energy loss. When you have work done transfer into the system, we say that it is energy gain, right? We have learned that in heat transfer as well. But in this case, when I have heat gain or heat loss, I know that it is this form of energy is being transferred in the form of thermal energy. But for work done, right, it is being transferred in due to a force that has been traveling over a certain distance. Okay, so most of the time when you want to use the term work done, you have to tell me that is work done, let's say this case is transfer in, work done by which force? Or if you do not want to refer the work done to the force that has created it, you can phrase it as work done on a particular object. So for example, in this case, is the ball that I'm launching into the air, right? As for work done in terms of energy transfer out, then the right way of describing this would be work done against a particular force. So this particular force can be friction, can be air resistance, can be many things, as long as it is a force. Okay, so let's try some of these structure questions and see how we can put this concept in action. So here, this question actually come from O-level 10-year series. You have a swimmer that push herself off and then launch itself. So it is very similar to this case, right? Instead of going up, you have the swimmer going towards the right, right? Instead of pushing against air, you have the swimmer pushing against water, right? The only difference is that for a ball, it doesn't have chemical potential energy in it. But for a swimmer, because she must have eaten something to grow to this size, there is chemical potential energy. So she can actually convert the potential energy and turn it into work done on herself. And then after that, the work done on herself will turn into kinetic energy, which will then enable her to move. And don't forget, as she is moving, she will also spend some energy to push the water, meaning that she will also transfer some energy to the water. So how do you describe the energy conservation that happens in figure 2? Now in physics, you need to pay very close attention to the number of objects that you want to describe. In this case, there are two, the swimmer and the water. So in this case, you start off with the chemical potential energy that's stored in her, right? So start off with your chemical potential energy, right, stored in her, and then you will convert this chemical potential energy into work done on the swimmer. So you transfer the chemical potential energy to this system, and this system consists of the moving swimmer and the stagnant water. So this work done that you transfer in, the system is the water and is the swimmer and the water, will then enable the swimmer to convert this into kinetic energy, right? And at the same time, it will also transfer some of this energy into kinetic energy to the water, because as you swim, you're going to push the water away, right? So the water will change its speed from 0 to a certain speed. So the water will gain Ke as well. Now another example, this one is also from a TYS. You have a child at the top of the slide, and basically the slide is moved from this point to this point. So you can assume that there's no air resistance as well. But between X and Y, it is rough. So there will be energy loss from the system. So in this case, the system that you are talking about will be the child, right? So at the beginning, the child would have GPE, and then as it slides down a smooth curve, down here at the bottom, it will have Ke, correct or not? However, as the child reaches X and goes to Y, this amount of Ke will become 0. So meaning that between here to here, there will be energy loss out of the system. So this one will be your work done, right? Because it's energy loss, then I will say that it is work done against. And I have to identify the force that caused this energy loss. In this case, obviously, it is friction. Right, so in my mind, this is the energy conservation diagram, and I need to verbalize it. So I will say that at the beginning, there will be a GPE, gravitational potential energy, store when the child is at the top of the slide. Well, this GPE within the system, when it reaches X, is converted to kinetic energy, right? And as the child moves from X to Y, which is the blue highlighted part, this kinetic energy will turn to 0. It then must mean that this kinetic energy must have been turned into work done against friction, right? And this work done against friction will then be subsequently converted into heat or other forms of energy. So it will be lost to the surrounding, right? Now I just want to highlight there is a difference if you interpret it this way. So this GPE, slide down, reaches X, then you reach here, KE becomes 0. Right, and this is the part. So some of you in your writing, you may say that, oh, as the child is moving along the rough surface, yes, there will be energy loss due to work done against friction, and then maybe it is due to typo, you will say, and it will lose energy as heat loss. Now this is wrong. Okay, this is wrong, because your heat loss, sound energy loss are all part of the work done against friction family. Before you can have heat, you must have energy loss due to friction first. Without friction, how can you generate the heat? Right? So because of that, just remember this work done as energy loss, right? Subsequently, it will be converted into heat. It can then be converted into sound and all sorts of other things. Okay, but work done is the main family. Okay, 2 more questions. So this is a O-level TYS question. So it consists of a gymnast and a stretch spring. So immediately when you look at this, you know that, oh, there are 2 bodies. Most likely there will be work done because then there's energy transfer. Well, at B, you can also observe that between A and B, actually the gymnast will gain GPE because now there's a height difference. And then after that, when it reaches C, it will gain even more height. So I think this story is about a gymnast gaining GPE. So if I want to draw the system, well, at the very beginning, right, my gymnast start off at H equals to 0, which is here. Right, then after that, the gymnast go up by a little bit, and it reaches B. And after that, the gymnast go up by even more, it reaches C. Right, and this is my isolated system, meaning that my gymnast is isolated. So when the gymnast converts itself, it means that now at H equals to 0, somehow it will gain at A, right? This is A. So at A, somehow the gymnast begin to gain energy. So cannot be, right? There must be an energy input, meaning that down here there must be some energy that has been transferred into my system, and this energy must be coming from the spring, right? So you can say that this one is either work done by the spring, or you can call this work done on the gymnast. Up to you. So after this work done by the gymnast, then obviously the gymnast will move, right? So we don't care what is going on in between. We are talking about the different points. So at B, then I would know that the gymnast must be moving, and the gymnast gained GPE, right? So this whole chunk of energy in yellow must be coming from this whole chunk of energy that is being transferred into the system. Correct or not? Then when it reaches C, it reaches maximum height in a one-dimensional motion. So therefore, down here, it will be only GPE. So now we agak-agak have a sensing of what we're going to write. So again, the question is to describe what happened to the energy between A, B, and C, right? So the spring, of course, it will spring elastic potential energy. And it will be transferred to the girl as either of them. You can call it work done by spring, or you can call it work done on gymnast or the girl lah. So of course, the girl, after receiving this bunch of energy, it will turn it into GPE, and it will turn it into kinetic energy at B, right? Because B gained the gymnast at B gained some height, and of course it is already moving, so it will have Ke gain. And at C, all the energy that it get from the spring, right, from the spring or even from whatever energy you have at B, will be completely converted into GPE, because at the top over here, she is no longer moving, right? It reaches the maximum height, is a point of U-turn. So that's question 3 for you. Okay, now this filling in the blank exercise allows you to practice to identify the types of energy, the form of the energy. But when you do it on your own, please be very mindful about the object, right? Are you talking about the spring gaining Ke, or are you talking about the girl gaining Ke? So you need to be mindful of the subject of your answer as well. Okay, finally, not finally, I think there's one more question, question 6. So for question 5, it is again a TYS question. You will have 3 pictures, but the question asks you to focus on only one, which is dealing the impact. And I just want to highlight to you down here, can you see that the golf ball has been deformed? So because of that, if there is deformation, this means that there will be energy stored as elastic potential energy. Well, so in this case, how will this work? You have a golf ball and it is resting, right? So basically down here, velocity is 0. Then after that, it will be hit. Then it will become like that, correct? And when it becomes like that, there is some form of EPE being stored here. During the impact, it has not started moving yet, right? And after the impact, then of course the ball is back round. There's Ke and there will be GPE, because as you can see, the ball gains some height. So if you look at the ball as the system, you can see that at the beginning, down here, your GPE is 0, Ke is 0. But at the second point, suddenly you will have some EPE. This means that the ball itself cannot convert anything to EPE, because there's no Ke and there's no GPE from the start. So it means that there must be an energy input, and this energy input will be the work done by the golf club, right? Where's the golf club? Yeah. Or if you do not like the word work done by golf club, you can say that, well, the kinetic energy of the club has been transferred to the golf ball, and the golf ball turns it into EPE, right? And once you have this energy transfer into the golf ball subsequently converts this energy into GPE and Ke. So now I need to describe the energy conservation during the impact. Well, first thing, I started off with this, right? So I need to mention that maybe I will start with this rather than this, right? The Ke of the club, when it impacts the ball, it will transfer energy to the ball as work done by the club or on the ball, and then the ball will turn this energy into EPE, and that's about it, right? Because the question only asks you to talk about this part, right? This part during impact. So let's try. So step 1, we would say that the Ke of the club is transferred to the ball as work done on the ball, right? If not, you can also call it work done by the club, up to you. Yeah. Then number 2, the ball deforms and store this energy. So this energy in English refer to the previous subject, right? we store this energy as elastic potential energy, and that is the end, right? Because this is during impact, right? The ball has not moved yet, and then it deforms. So I think this is the last one. Right? I tried to combine the idea of CG with some thinking logic. Okay, so there's a mini clock down here which is vertical. Minute hand has a mass, then this means that there will be weight lah, right? And it takes 1 hour to make one complete rotation, obviously. The CG of this is 0.95 meter from the center of the face. So if you have a minute hand pointing down, the CG of the minute hand will be 0.95 away from the center of the face. So this is 0.95 meter. Okay. Then it says in this question, I will neglect effect of friction, meaning that there is no work done against friction. In another word, it means there's no energy loss, and this includes the effect of air resistance. So basically no energy loss. Work is done by the clock's mechanism to raise the minute hand during the part of rotation, and I'm asked to describe the energy conservation when lifting the minute hand from pointing vertically downwards, which is what I've drawn here, to vertically upwards. So vertically upwards will look like this, and the CG will be over here. So I'm having these two. So basically what I have is that I have a system whereby the object started at h equals to 0. Somehow after half an hour it appears here, whereby h is 0.95 times 2. Okay, my mental calculation not very correct. So if you look at this isolated system, then you find it very strange, right? At time equals to 0, you are here, but at time equals to 30 minutes, you are on top. So that means there must be some energy input, right? If not, how can the height just change like that? So this energy output will be the work done by the clock mechanism. How do I know I should phrase it this way? It is right here. So that is what happened when the clock down here, it must have gain GPE, right? So where does this gain in GPE come from? It must come from the work done by clock mechanism. So to describe this, very simple, right? There is energy transfer to the minute hand, okay, in the form of work done by the clock mechanism, right? This energy is converted to GPE when the minute hand is raised 0.95 times 2, that will be 1.8 meter higher. Oh, raised, that can already, done already, right? So basically this entire worksheet is to be here to actually, how to put this, is to show you how you can describe energy conservation when you are given a certain system. And as you can see, if you recap, mainly there are only four types of energy, right? Within the system itself, there will be some change between GPE and KE. But in order for it to start, sometimes the question context will give you another object or another force that will actually transfer energy into the system, and your job is to be able to phrase this as work done by, work done on, things like that. And sometimes the context will also involve energy loss, and your job is to identify this as work done against a certain force. And remember, heat and sound is a subsidiary of this work done against friction or against air resistance. So thank you, and if you have any question, do WhatsApp me. Do not hesitate and wait and regret about it after the test. Okay, always clear all your doubts before the test. Okay, thank you.